Now here's the exciting thing. Right now, the one thing you should be 100% certain on is that the area under a velocity curve gives distance traveled. But there's a relationship between distance and velocity. We know that velocity is the derivative of distance, of position. It turns out that you can find the area under any derivative curve, a rate of change curve, to figure out how much the original function has changed over that time interval. So here's an example of a problem. It was a multiple choice question. I didn't give you the multiple choice options, but that makes it a little bit easier. The production rate of cola in thousands of gallons per hour at the production plant is shown in the graph. To the nearest round number, how many thousands of gallons of cola were produced that day? So notice here along the input axis, you can see if that's an S or a T, or so this is measured in hours. And that's hour 0 is midnight to midnight on July 1st to 24 hours later, 11:59 on July 1st. And the outputs are measured in thousands of gallons per hour. So gallons per hour times 1,000. We can actually now answer this question. If C were the amount of cola produced, this is a graph of C prime, the rate at which cola is produced. It's a rate because it's measured in thousands of gallons per hour. So this is a graph of C prime. Their question is how much cola gets produced. We're going to find the answer by finding the area under the C prime curve. So notice, we were not asked to do specifically a rectangular approximation method. I don't know a formula for the area under this curve, but we've been asked to approximate, and it's a multiple choice question. We're just going to do our best counting boxes. So how many full boxes, so squares that are 6 hours times 100,000 gallons per hour of cola. So I'm just going to show you how I would count this. I would say this is 1 box, 2, 3, 4. When I say box, I mean rectangle. 5, 6. Here is almost a 7th box if I combine it maybe with that leftover piece. Here's an 8th box. So how many rectangles fit under the curve? 8. Each rectangle has a width of 6, I'm going to put hours, and a height of 100,000 gallons per hour. So I'm going to do all this multiplication. Notice the hours in my units are going to cancel. 8 times 6 is 48. 4,800,000 gallons per hour is going to be my answer. So 4,800 and then 1,000 gallons. Be really careful about the units. The units have to make sense or you've done it wrong. The width of each rectangle is measured in hours. The height is measured in gallons per hour. The hours cancel, which give us gallons, or thousands of gallons is the unit. And we have to check and make sure that makes sense. If I'm producing cola, does it make sense to produce, if I ask how much cola is produced, does it make sense to give my answer in gallons? And it does here. So here's a problem you've actually already seen. I modified it, or I used a different part in your last test. Here we have a hot air balloon that's inflating, so the radius is increasing as the hot air balloon is inflated. I know that R is concave down, and here I have selected values of R prime. Use an R-RAM approximation to find out how much the radius has changed. So I want to find out how much R has changed over the intervals 0 to 12. Well, I can find out the change in R by finding the area under the R prime curve. R prime is measured in feet per minute. Time is measured in minutes in this case. So if I add up areas under the R prime curve, I'm going to have units of feet, so feet per minute times minutes, feet, which makes an appropriate unit for measuring the radius. So here I don't actually have an R prime function, but I have enough that I have information in a table which I can use to find areas of rectangles. So here I'm going to use, oops, that's not the right notation. I'm going to use what's in the table to help me figure out how much R has changed. So over the first 2 minutes, I've been asked to use RRAM, so I'm going to use the data from the right-hand end of that interval. So 0 to 2 is the interval that the first rectangle is going to cover. The right-hand endpoint of 0 to 2 is 2. So I'm going to use the value, the function value, the R prime value, when time is 2. So this is going to be 2 times 4 plus, how long is this interval? How wide is the rectangle that covers from 2 to 5? Well, the difference between 2 and 5 is 3. That was a plus sign, just to clarify here. Plus 3 times the right-hand end of that interval is time equals 5, so I'm going to use this 2.0 plus the next time interval goes from 5 to 7, so how wide is that rectangle? 7 minus 5 is 2. And then the height of that rectangle is going to be the right-hand R prime value, which is 1.2, plus the next interval covers from 7 to 11. From 7 to 11, the width of that rectangle is going to be 4. I'm going to use the R prime value 0.6 because that's from the right-hand end of the interval, plus the last interval covers from time 11 to time 12. That's only 1 minute wide, so 1 minute times the height's going to be 0.5. So I can conclude that over the time interval 0 to 12 minutes, the radius increases by about 19.3 inches. Notice that's different from giving an estimate of the value of the actual length of the radius after time 12. Because, notice here, when we start the problem, the radius of the balloon is 30 feet. Then over the time interval 0 to 12, it's going to increase about 19.3 inches. If you were asked to give an estimate of R of 12, you would say the estimate is about 30 plus that 19.3, which is 49.3. What are the units? Each one of these rectangles was a time times the rate in feet per minute. So minutes times feet per minute makes feet. So feet plus feet plus feet plus feet plus feet. Looks like I got this wrong here. That should be feet. R of 12, the radius at time 12 is approximately equal to 49.3 feet.